Another way in which light can become polarized is through reflection. So when light reflects off of a material with a high index of refraction, then light is often polarized horizontally by that reflection. So the light that comes off, here we have some incident beam, which is unpolarized, and then after reflection off of maybe a surface of some water, then the light is polarized so that the direction of electric field oscillation is horizontal. So basically it's pointing right out at you from the screen and directly away from you. Complete polarization occurs when the angle between the reflected and the refracted light is 90 degrees. So we can see the condition for complete polarization given here. Here's the reflected beam, here is the refracted beam, and the reflected beam is completely horizontally polarized when this angle here is 90 degrees. So we can use that to find out what the angle of incidence must be. So if we use Snell's law, then n1 times the sine of this completely polarized angle is going to be equal to n2 times the sine of theta 2. Now we can look at the angles involved in our problem. We know that the polarized angle, this incident angle will be equal to this reflected angle, so this theta p will be equal to this one, and this angle plus the 90 degrees plus theta 2, all of that's going to add up to 180. So if we rearrange this expression a little bit, theta 2 is going to be 90 degrees minus the sine of theta p. So we can replace theta 2 in our Snell's law expression. We can replace that theta 2 with 90 minus theta p, and then if we go and use some of our trig identities, we'll find that this is equivalent to the cosine of theta p. So then we can, if we rearrange this expression for the ratio of the indices of refraction, then that's going to be equal to sine theta p over sine theta 2, but we said that sine theta 2 is equivalent to cosine of theta p for this condition where we have this 90-degree angle here, and the sine over the cosine of the same angle is equal to the tangent. So this is Brewster's angle. It's known as Brewster's angle, and it tells us the incident angle for which we get complete horizontal polarization of light. Even if we're not exactly meeting Brewster's angle, this condition, then at least some of the light will be horizontally polarized. And so that's why if you have sunglasses that are polarized, the transmission axis is actually vertical, so that any reflections off of either water or pavement or things like that, they will tend to be horizontally polarized, and to reduce that glare, you have sunglasses with a vertical transmission axis. You can also use polarizing filters on cameras if you want to take pictures of water, and you can see here is a picture where without the filter you get a lot of glare off the water. You get a lot of reflection, but you can reduce that reflective glare by using a filter with a transmission axis that is vertical. So all of the horizontally polarized light, which is reflecting off the surface of the water, is blocked by the filter. The third way in which you can get polarization is through scattering. So vibrating air molecules will polarize light, and so light that scatters around through the atmosphere can become polarized with this process. Another thing to be aware of with polarized light is optical activity. So there are substances that have the property of optical activity, and they will rotate the direction of polarization. So if you start out with some unpolarized light and you put it through a Polaroid so that it's polarized, then if you put it through an optically active material, that material can rotate the polarization axis. And some materials, such as corn syrup, actually have this property where they can rotate the axis of polarization. Polarizing microscopy is useful for some applications involving birefringent materials. So With birefringence, the index of refraction differs for differing polarization angles. So if you have a birefringent material and you use polarized light to examine that material, then you can get features showing up that would not be visible otherwise. So for example, here's a sample and you can see that there's this buildup of urate crystals. So these urate crystals have built up in this person's joints, and you can see they're very sharp. They're actually needle-like, and that causes gout, which is quite painful. So normally, with just using light, these urate crystals wouldn't be particularly visible, but using polarized light enhances their image, and so that you can see them in the sample. So let's next consider this question. We have an unpolarized light source shining through two polarizers. The first polarizer is aligned along the y-axis, and the second is 45 degrees away from the y-axis. What is the ratio of the final to the initial intensity?